A single thread drifting through space could possess enough power to cut our world in two. These are cosmic strings, and they might be the most dominant objects in existence. By the end of this journey, you will see the universe's fundamental power in a completely new light. How did flaws in the fabric of reality form just after the Big Bang? And what would happen if you encountered one? The answers challenge everything we know about space, time, and energy. What does true power in the cosmos look like to you? Our universe began not with calm, but with chaos. In its very first moments, everything that exists was compressed into a searing, unimaginably hot point. Then it expanded and began to cool, a process so violent and rapid it defies human comprehension. Think of this cooling not as a smooth slide, but as a series of sudden, jarring shifts, much like water abruptly freezing into ice. When water freezes, the molecules snap into a rigid, crystalline structure. But this process is never perfect. Trapped air bubbles form or cracks appear in the ice. These are imperfections frozen into the new state of matter. The infant universe underwent its own version of this. As it cooled, the fundamental forces that govern reality, like gravity and electromagnetism, were born, separating from a single, unified force. This separation was a cosmic phase transition, a shudder that ran through the fabric of everything, and just like in freezing ice, this process was not flawless. In the frantic rush to settle into a new, stable state, defects formed. These were not cracks in ice, but cracks in spacetime itself. Cosmic strings are one such defect. They are not made of atoms or any matter we recognize. They are pure energy, flaws in the universe's structure, threads of trapped primordial power that were literally frozen in place as the cosmos cooled. This makes them something truly extraordinary, fossil records of the universe's infancy. They are relics from a time of almost impossible energy, preserving a snapshot of the universe when it was less than a second old. So what would you be looking at if one drifted by? A cosmic string is not a string you could ever touch or see in the conventional way. It is a one-dimensional crack in the fabric of spacetime itself. Think of the universe as a vast, perfect sheet of ice. A cosmic string is like an infinitely long, impossibly thin scratch etched into that ice, a flaw frozen into the cosmic crystal. This is a line where the normal rules of physics simply do not apply. The energy trapped within this flaw is beyond human scale. Its mass is so densely concentrated that a single inch of it could outweigh entire mountain ranges on Earth. This transforms the idea from a wild theory into something with tangible, terrifying properties. It is a physical object with length, but with no measurable width, a singularity stretched into a line. If you were to circle one, you would find that the total distance around it is less than it should be, as if space itself has gone missing. This is not an empty void, but a scar of pure, concentrated power left over from the birth of everything. This perfect symmetry could not last. The universe was like a hot, perfectly round balloon, uniform in every direction. But as it expanded and cooled, that flawless symmetry had to break. The forces that were once unified began to differentiate, a process physicists call symmetry breaking. It is the same principle at work when a hot, liquid metal cools into a solid crystal. The liquid is symmetric, the same in all directions, but the crystal that forms has a specific, rigid structure, breaking that initial symmetry. In that moment of transition, when one state gives way to another, defects are inevitable. Think of bubbles trapped in ice or the cracks that form in drying mud. the universe, in its frantic cooling, experienced its own colossal phase transition. And in some of the most compelling theories, the cracks that formed were not in mud or ice, but in the vacuum of spacetime. These cracks are cosmic strings. They are not made of particles, but are topological defects, imperfections frozen into the very geometry of the cosmos. This is the profound link between the microscopic and the macroscopic. The abstract rules of high-energy particle physics, governing the universe when it was less than a second old, dictated the formation of objects that could one day shape the largest structures we see, galaxies and clusters of galaxies spanning millions of light years. The birth of a cosmic string was a quantum event with truly cosmic consequences. Their width is a concept that strains the limits of physics. A cosmic string possesses no width in any way we can meaningfully measure, a one-dimensional line in a three-dimensional world. Yet its length defies all sense of scale. A single string could be as long as the entire observable universe, a thread of pure energy stretching across billions of light years. It might form a loop larger than a galaxy, or run straight through the cosmic void like an infinite fault line. This creates an object of impossible proportions, thinner than a subatomic particle, but longer than any galaxy cluster. And within that impossible line, the energy is packed to an almost absurd density. Just a few miles of cosmic string could hold more mass than our own sun. Let that sink in for a moment. The sun contains 99.8% of all the mass in our solar system. Its gravity holds planets in stable orbits across billions of miles. And the equivalent of that entire colossal mass could be squeezed into a length of string no longer than your morning jog. This is not just a lot of power, it is power concentrated into a form so extreme it challenges our very definitions of an object. This incredible scale is precisely why cosmic strings, even as theoretical constructs, command such awe. An entity that is both everywhere and nowhere, with the mass of a star packed into a thread, truly earns the title of a candidate for the most powerful object in existence. This immense concentration of energy means a cosmic string is a gravitational titan. We often think of gravity as a force that pulls things together, but the reality described by Einstein is far more strange. Mass and energy do not pull, they bend. They warp the very fabric of spacetime, and objects simply follow the curves created. A cosmic string with a linear density so extreme a single mile could outweigh our sun creates a warp unlike anything else. It does not behave like a planet or a star, pulling matter into orbit or crushing it into a sphere. Instead, its gravitational influence is a sharp, precise fold. The geometry of space around a string becomes conical. Picture a perfectly flat sheet of paper. Now, if you cut out a single, thin slice from its center and tape the edges back together, the paper would form a shallow cone. This is exactly how a cosmic string warps the universe. It removes a slim wedge of space itself, stitching the edges back together seamlessly. The result is not a downward pull, but a missing piece of reality that distorts the paths of anything traveling near it. This leads to one of the most incredible predictions, a phenomenon called double imaging. Two beams of light traveling perfectly parallel to each other pass on either side of a cosmic string. From our perspective, they should remain parallel forever, but because the space around the string is conical, these two straight paths are bent toward one another. They converge. To an observer, it would look as if a single distant star or galaxy was in two places at once, a ghostly gravitational mirage proving that the fabric of space itself has been subtly torn and repaired. This is the quiet, profound power of a cosmic string, a flaw in reality so potent it can split light itself. This ability to split light makes cosmic strings some of the most unusual lenses in the universe. Gravitational lensing is a familiar concept where the immense gravity of a galaxy cluster bends the light from objects behind it, creating arcs and smears in our telescopes. A cosmic string, however, creates a lensing effect that is far more precise and far stranger. Because its gravity folds space into a perfect cone, it does not blur or distort the light. Instead, it cleanly slices the image. If a long, straight cosmic string were to drift directly between our telescopes and a distant, single galaxy, we would not see one galaxy. We would see two. These would not be blurry copies, but perfect mirror image duplicates of the same galaxy, separated by a thin, dark line, the shadow of the string itself. It would be as if the universe itself had developed a crack, and we were seeing the light from the other side split as it passed around the edges. For astronomers, this is the ultimate prize, a signature so clear and distinct it could not be produced by any other known object. The hunt is on for these phantom pairs in the deep field surveys of the cosmos. They are searching for the perfect cosmic alignment, a string, a distant quasar, and our line of sight all coming together to reveal a flaw in reality. Finding that double image would be more than just a discovery. It would be a direct observation of the universe's primordial structure, a fossil from its first moments made visible. This energy density is almost impossible to grasp. Imagine a single meter of thread, thin enough to be invisible to the naked eye. Now, compress the entire mass of our planet, every mountain, every ocean, every continent, into that minuscule length. This is the raw, staggering power contained within a cosmic string. The energy is not like anything we can create or contain. It is not the explosive force of a nuclear reaction, nor the chemical energy stored in fuel. This is energy woven directly into the vacuum of space, a fundamental tension that was locked into the universe's structure as it solidified from its primordial state. This single property is the engine behind every incredible phenomenon a cosmic string might produce. That unimaginable concentration of mass energy is what warps spacetime into a cone, creates gravitational mirages, and could theoretically distort the flow of time itself. If you were to move at a significant fraction of light speed alongside a cosmic string, the rules of relativity tell us that time would pass more slowly for you compared to the rest of the universe. This time dilation would be a direct result of the string's immense gravitational field, a field generated not by a vast sphere of matter, but by a thread thinner than an atom. This energy, frozen in place since the beginning of time, is what makes these cosmic flaws candidates for the most powerful objects in existence. They are not just relics, they are active, dynamic engines of pure potential. This distortion of space inevitably warps the flow of time itself. According to Einstein's theories, gravity does not just bend the paths of planets and light, it also stretches and slows time. A clock placed in a stronger gravitational field will tick more slowly than one in empty space. This effect is subtle on Earth, but near a cosmic string, it becomes profound. The string's immense linear density creates a gravitational field so intense that time would slow to a crawl in its immediate vicinity. Imagine a hypothetical starship, its hull humming as it maintains a stable orbit just a few miles from one of these threads. For the crew on board, life proceeds at a normal pace. They eat, sleep, and conduct their research, their clocks ticking away second by second. But with every orbit they complete, a strange phenomenon unfolds. While only a single year passes for them on their ship, back on Earth, or anywhere else in the universe far from the string, decades, even centuries are rushing by. The crew would return from their mission to find a future they never knew, their own civilization transformed beyond recognition. This is not the stuff of science fiction, but a direct, sobering prediction of general relativity. The environment around a cosmic string could create a time-warping effect so extreme it would make the gentle slowing of time near a planet like Earth seem utterly insignificant. In fact, because a cosmic string lacks an event horizon, a spacecraft could theoretically orbit it and experience this extreme time dilation without being irretrievably crushed or trapped. This makes these cosmic flaws not just relics of power, but potential engines for the most dramatic time travel imaginable, a place where the very tick of the clock is dictated by a crack in the universe's foundation. But the influence of a cosmic string does not end with bending light or warping time. These relics are also capable of setting spacetime itself into motion. Any object with mass that accelerates creates ripples in the fabric of the cosmos, waves of gravity that travel outwards at the speed of light. We have detected these gravitational waves from the collisions of black holes and neutron stars, but these events are fleeting. A cosmic string network, however, would be a continuous, thrumming source of these vibrations. Imagine a string loop larger than a solar system, vibrating wildly. Or picture two such loops colliding and merging, releasing a catastrophic burst of energy. These are not gentle ripples. They would be tsunamis in the medium of spacetime, propagating across the entire universe. This is where theory meets our most advanced technology. Observatories like LIGO and Virgo are listening for the faint whispers of these cosmic disturbances. The unique signature of a snapping cosmic string or a colliding loop would be unmistakable, a sharp, singular chirp in the data, unlike the merger of two black holes. Finding that signal would be a direct detection, not just of a massive object, but of a fundamental flaw in reality shaking the universe. It would open an entirely new window into the first moments of creation, allowing us to hear the echoes of the cosmos as it solidified, listening for the tremors from cracks that have existed since the beginning of time. These vibrating loops are not serene cosmic ornaments. They are whips of pure energy, lashing through the void at speeds approaching that of light. The physics governing their motion is a violent ballet of tension and velocity. A single loop, perhaps larger than our entire solar system, does not simply spin. It oscillates, folds, and crosses over itself in a chaotic, relativistic dance. This frantic motion is not without consequence. Every whip crack, every sharp turn sends powerful ripples cascading outward. These are gravitational waves, and for a cosmic string loop, they are the very breath of its existence. The loop loses energy with every vibration, radiating its immense power away into the fabric of spacetime. This slow, steady drain causes the loop to shrink, gradually diminishing in size over millions of years. Think of a bell struck once, ringing with a clear, pure tone that slowly fades into silence. A cosmic string loop is that bell, but its tone is a fundamental vibration of gravity itself, and its fading ring is the slow evaporation of a primordial defect. This entire life cycle, from its formation in the early universe to its final, silent dissolution, is a key to unlocking one of cosmology's great mysteries. The collective hum of all the string loops that have ever existed and evaporated would create a permanent, low-frequency rumble permeating the cosmos, a gravitational wave background. Detecting this faint signal would be like listening to the universe's fossil record, a direct echo of its tumultuous birth and the dynamic lives of its most powerful and most ephemeral structures. This collective hum of vibrating strings would form a permanent soundtrack to the cosmos, a stochastic gravitational wave background. Unlike the violent chirps from black hole mergers, this signal is a low, steady rumble, a cacophony of countless loops oscillating and colliding across space and time. It is the gravitational equivalent of the cosmic microwave background, that faint afterglow of the Big Bang we see as static on our television screens. But while the microwave background is a fossil of the universe's fiery infancy, a snapshot from when it was 380,000 years old, the gravitational wave background would be a relic from a far more primordial era. It would carry whispers from the universe's very first second, a time so early that no light could yet travel freely. This makes it our only potential window into that initial, unimaginable moment of creation. Detecting this faint whisper is one of the most ambitious quests in modern science. Observatories on Earth, like LIGO, are not yet sensitive to the incredibly low frequencies of this primordial hum. The hunt requires thinking on a galactic scale. Scientists are using pulsars, the rapidly spinning corpses of dead stars, as a galaxy-sized detector. These pulsars act as incredibly precise cosmic clocks, their radio beams sweeping past Earth with metronomic regularity. By meticulously monitoring an array of these pulsars for decades, astronomers are listening for the slightest correlated deviations in their ticks. A passing gravitational wave background, the collective sigh of all cosmic strings, would stretch and compress the space between us and these pulsars, minutely altering the arrival times of their signals. Finding that specific, correlated pattern in the noise would be a discovery of monumental proportions. It would not only confirm the existence of cosmic strings, but would hand us a recording of the universe's birth cries, allowing us to listen directly to the physics of its very first moments. But perhaps the most profound legacy of these cosmic strings is written across the sky in the form of galaxies themselves. The universe we observe is not a random scattering of stars. It is a vast, intricate web of galaxies, clustered into immense walls and filaments surrounding great voids. How did this cosmic architecture arise from an almost perfectly smooth, hot beginning? One compelling answer points directly to those primordial flaws. The immense gravitational wells of cosmic strings would have been the first structures to form in the early universe. Picture a universe still dark, filled only with a smooth, diffuse soup of dark matter and hydrogen gas. Then a single cosmic string, a thread of unimaginable density, drifts through this primordial fog. Its gravity is not a gentle pull, but a sharp, deep fold in spacetime. This fold acts as a cosmic seed. Dark matter, which responds only to gravity, begins to cascade into this gravitational pit. Normal matter follows, piling up along the length of the string like dew collecting on a spider's web. In this theory, these cosmic strings were the scaffolds upon which the first proto-galaxies were built. They drew the blueprints for the entire cosmic web, providing the initial imperfections that gravity could amplify into the galaxies and clusters we see today. This idea presents a fascinating alternative to the standard story of cosmic structure. The prevailing theory relies on quantum fluctuations during a period of rapid inflation, tiny ripples that were stretched to cosmic proportions. But the cosmic string model offers a different kind of architect. Instead of faint ripples, the universe used colossal, one-dimensional cracks as its foundation stones. The search for the origin of cosmic structure is in many ways a search for the universe's first seeds. Did they emerge from the quantum foam, or were they literally carved into the fabric of reality as it cooled? Finding evidence for cosmic strings would not just add a new object to the cosmos, it would rewrite the first chapter of how everything we see came to be. This invisible scaffolding of the cosmos points toward an even deeper mystery. We know that the gravity holding galaxies together comes from something we cannot see, a substance we call dark matter. Its nature is one of the most profound puzzles in all of science. What if cosmic strings are not just the architects of structure, but are also a part of this hidden cosmic ingredient themselves. While the leading theories for dark matter involve new, undiscovered particles, the possibility that cosmic strings could contribute is a compelling and exotic alternative. Think about their fundamental properties. They are not made of atoms, they are incredibly stable over billions of years, and they interact with the universe almost exclusively through gravity. This sounds remarkably similar to the description of dark matter, a network of string loops scattered throughout the universe since its beginning would be completely invisible to our telescopes, yet their collective gravity would be immense. They would weave through galaxies like ghostly threads, adding their unseen mass to the gravitational glue that keeps stars from flying apart. This idea pushes the very definitions of matter and energy. We are used to thinking of matter as being made of particles, things you can theoretically count, but a cosmic string is a defect, a flaw in the vacuum. It is a different kind of stuff altogether, a form of concentrated energy that behaves like mass. Could the missing 85% of the universe's matter be composed, at least in part, of these cosmic cracks? It is a long shot, but it forces us to ask a more fundamental question. What truly is matter? Is it only the particles we can list, or can the very geometry of space, twisted and knotted from the beginning of time, also account for the weight we feel but cannot see? This vast cosmic web would be a dynamic and ever-changing structure. The network is theorized to be a tangle of infinite strings stretching across the universe, interspersed with countless closed loops of all sizes. These are not static sculptures, they are a chaotic, living system. The strings whip through the void at relativistic speeds, constantly crossing paths. When two strings meet, they can do one of two things. They might simply pass through one another, a ghostly intersection, or far more dramatically, they can reconnect. Picture two vibrating violin strings slicing through the air. If they touch, they can bind together at that point, instantly reshaping their entire structure. This process, called intercommutation, is the engine of the network's evolution. An infinite string might snag on itself, pinching off a colossal loop that spins away on its own. Two loops could collide and merge into a larger, more complex shape. This endless dance of splitting and merging is what keeps the cosmic web alive, a self-sustaining ecosystem of defects. To understand this chaos, scientists turn to supercomputers. They run simulations that model the physics of these strings, starting from the early universe and watching the network evolve over billions of years. The digital cosmos that emerges is breathtaking. It shows a universe crisscrossed by these brilliant, energetic threads, a web of power where loops are constantly born, vibrate, and fade away. These simulations are not just pretty pictures, they make specific predictions. They tell us how many loops of a certain size we should expect per cubic volume of space. They predict the specific frequency of the gravitational waves these loops would emit. This is the crucial link between a beautiful theory and a tangible observation. By understanding the network's behavior, we know what to look for in our telescopes and our gravitational wave detectors. The faint hum we hope to hear is not from a single string, but from the chorus of an entire network, a symphony of cracks in spacetime that has been playing since the first second of existence. Finding a crack in reality requires looking for the shadows it casts. Astronomers are not searching for the string itself, but for its unique fingerprints on the cosmos, using three powerful methods to track this phantom. The first is the hunt for those perfect double images. Telescopes like the Hubble and the upcoming James Webb Space Telescope scan the deep fields of the universe, analyzing millions of galaxies to find a pair that is a perfect mirror match in every way: brightness, color, and age, separated by a thin, dark line of nothingness. It is a search for a cosmic coincidence so precise it could only be explained by a cosmic string acting as a gravitational razor blade, cleanly splitting the light of a single object. The second method looks at the oldest light we can see, the cosmic microwave background. This faint glow is the cooled remnant of the Big Bang's fireball, and it holds an imprint of every structure that existed when the universe was young. A cosmic string with its sharp gravitational fold would have left a distinct scar as it moved through this primordial plasma. It would create a very specific, line-like discontinuity in the temperature of this background radiation, a cold streak etched across the sky. The third and perhaps most promising method is to listen. Gravitational wave observatories are tuned to hear the universe's vibrations. A cosmic string network would produce a continuous hum of gravitational waves, but it would also produce sharp, singular events. The most dramatic would be the snap of a string loop. When a vibrating loop reaches a certain point of instability, it can pinch off, its ends reconnecting and releasing a catastrophic burst of gravitational energy, a loud, high-frequency chirp in the cosmic quiet. Each of these methods is a different kind of fishing line cast into the deepest ocean. One looks for a perfect reflection, another for a fossilized scar, and the last for an echo of a violent tremor. Catching just one of these signatures would do more than confirm a theory. It would open a direct window into the universe's first moments, allowing us to witness the frozen flaws of its violent birth. The faint static glow of the cosmic microwave background is our oldest photograph of the universe. This afterglow, a snapshot from when the cosmos was just 380,000 years old, holds the frozen imprint of every structure that existed at that time. A cosmic string drifting through this primordial plasma would have left a unique and indelible mark. Its sharp, conical gravity would have tugged on the hot, dense matter, creating a very specific kind of scar. As the string moved, it would have generated a step-like discontinuity in the temperature of this background radiation. Think of it as a line drawn across the sky where the temperature on one side is minutely colder than the other, a perfect linear crack in the universe's oldest light. This is the kind of clean, theoretical signature that astronomers dream of finding. The European Space Agency's Planck satellite, one of our most powerful observatories for studying this ancient light, meticulously mapped the entire sky in search of these subtle steps. Its sensitive instruments scanned for any thin, straight lines of temperature change that could not be explained by any other known process. The result of this immense search was silence. No definitive cosmic string signature was written in the CMB's faint whisper. Yet this absence is not an ending. It simply tells us that if these strings exist, their network is sparser than we once hoped. The hunt now refines its focus, looking for fainter signals or different types of defects. Finding that single, cold line etched across the cosmos would be more than just a discovery. It would be a direct snapshot of a cosmic string's interaction with the infant universe, a moment frozen in time from an era before the first stars were born. The most powerful particle accelerator on Earth might seem insignificant compared to the universe's violent birth, yet it could hold the key to creating a microscopic echo of these cosmic flaws. The Large Hadron Collider slams protons together at velocities approaching the speed of light, recreating for a fleeting instant the searing temperatures that existed a fraction of a second after the Big Bang. In these microscopic fireballs, the fundamental forces of nature could momentarily unify, and as this energy dissipates, it might undergo its own rapid phase transition. This is the theoretical possibility that the vacuum of space itself could momentarily crack under the strain, forming a tiny, unstable defect. It would not be a cosmic string spanning galaxies, but a transient string-like object, a proof of concept flaw in the fabric of reality. The energy required to sustain even this miniature version is staggering, and the defect would evaporate almost instantly, but its brief existence would send a detectable shockwave through the detector. Scientists would be looking for an event so extraordinarily energetic and specific that it could not be explained by the production of any known particle. Observing such a phenomenon would be nothing short of revolutionary. It would provide the first experimental evidence that the universe's fundamental symmetries can break in this specific, defect-forming way. We would have recreated, in a controlled experiment, the very process that may have knitted the cosmos together, offering a direct, microscopic glimpse into the forces that shaped everything. These theoretical threads weave through our most ambitious models of reality. The very idea of cosmic strings finds its roots in grand unified theories, which seek to describe a profound moment in the universe's history. Just after the Big Bang, three of the four fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, were believed to be a single, unified interaction. Grand unified theories are the mathematical framework that attempts to describe this merger. As the universe expanded and cooled, this perfect symmetry broke, and the forces we recognize today froze out into their distinct identities. Crucially, these theories predict that such a phase transition would not be smooth. The breaking of this perfect symmetry would inevitably create defects, and one of the most stable types of defect is a one-dimensional line of trapped energy. A cosmic string, so within the mathematics that tries to unify the forces governing atomic nuclei and electricity, these colossal flaws are not just possible, they are a natural, expected consequence of a cooling cosmos. This gives them a firm foundation in the physics of the very small, yet their influence spans the largest scales imaginable, creating a breathtaking bridge between particle physics and cosmology. The same equations that describe the behavior of subatomic particles also predict the existence of objects that could shape entire galaxies. This connection is made even more compelling by an even deeper theory. Superstring theory, a leading candidate for a theory of everything, proposes that the fundamental constituents of the universe are not point-like particles, but incredibly tiny, vibrating loops of energy. These are the fundamental strings of the theory. While these are minuscule, far smaller than an atom, the theory also allows for the existence of much larger, macroscopic strings. These would be the cosmic strings we have been discussing. In the language of string theory, they are different vibrational states of these fundamental strings, stretched to cosmic proportions by the expansion of the universe. So we have two completely different, yet profoundly successful, theoretical frameworks, both pointing toward the same incredible conclusion. From the grand unification of forces to the vibrational nature of reality itself, the mathematics consistently suggests that one-dimensional cracks in spacetime are not only possible, but inevitable. This dual appearance across disparate theories lends a powerful credibility to their existence. It is as if two different maps of an unknown continent, drawn by different explorers, both clearly mark the same mysterious mountain range. The convergence is too striking to ignore, suggesting we are on the verge of a discovery that could unite the quantum world with the cosmic expanse. The final moments of a cosmic string loop are anything but peaceful. After billions of years slowly vibrating its energy away, a shrinking loop reaches a critical threshold. Its tension becomes unbearable, and the entire structure undergoes a catastrophic collapse. In a literal flash, the immense energy frozen within its length since the beginning of time is unleashed in a single, violent burst. This is not a slow evaporation, but a detonation. The energy released in that final instant could outshine entire galaxies. a transient fireball of pure, fundamental power. This staggering possibility offers a solution to one of astronomy's most enduring puzzles, the origin of gamma-ray bursts. These are the most luminous explosions in the universe since the Big Bang itself, fleeting flashes of high-energy radiation that appear randomly in the sky. We know some are caused by the collapse of massive stars or the merger of neutron stars, but the very brightest and most energetic ones remain mysterious. A decaying cosmic string loop could be the engine. As it snaps, the unfathomable energy stored in its structure would be converted directly into a jet of radiation and particles, a beacon of primordial fury visible across the cosmos. This transforms our view of these strings from silent fossils into potential cosmic arsonists, capable of igniting the most powerful blasts we can observe. Their death throes could be the birth cries of the universe's most extreme phenomena, written in light. That final, violent flash of a dying string loop is a glimpse of energy so extreme they defy our current laws of physics. We are venturing into a domain where gravity ceases to be a gentle curve and becomes a churning quantum foam. This is the Planck scale, a realm of such inconceivably small distances and high energies that the very concepts of space and time break down. At this fundamental level, the smooth geometry described by Einstein's general relativity must merge with the probabilistic, fuzzy world of quantum mechanics. For decades, unifying these two pillars of physics has been the single greatest challenge in theoretical science. We lack a complete theory of quantum gravity, and without it, our understanding of the universe's birth and its most extreme objects remains incomplete. This is where the cosmic string transforms from a mere object into something far more valuable. Its core is a singularity of pure energy, a line where the density approaches the Planck scale itself. A cosmic string is not just a relic of the past, it is a natural laboratory engineered by the universe in its first moments, designed specifically to probe the union of the very large and the very small. It is a ready-made experiment waiting for us to learn how to read its results. Think of our current dilemma. To study quantum gravity in a lab on Earth, we would need a particle accelerator the size of a galaxy, capable of reaching energies 1 trillion times greater than the Large Hadron Collider. It is an utterly impossible task, yet the universe in its infinite ingenuity may have already built this machine for us. A cosmic string is that accelerator, frozen in time and stretched across the cosmos. Its immense tension and energy density create conditions at its heart that we could never hope to replicate. By observing how a cosmic string behaves, how it vibrates, how it gravitates, how it eventually decays, we could see the fingerprints of quantum gravity imprinted on its existence. For instance, how would the fuzzy, quantized nature of spacetime, as predicted by loop quantum gravity, affect the way a string oscillates? Would its gravitational waves carry a unique signature, a subtle quantization in their frequencies that betrays the graininess of space itself? Or, from the perspective of string theory, could we detect the specific vibrational modes of a fundamental string that has been magnified to cosmic size? Each ripple, each snap, each gravitational whisper from a cosmic string would be a data point from the Planck scale, a message from a domain we cannot otherwise access. Finding and studying a cosmic string would not just confirm one theory over another, it would provide the first experimental evidence to guide the entire field. It would tell us which mathematical approach to quantum gravity, be it loop quantum gravity, string theory, or another idea entirely actually describes our reality. The cosmos built this laboratory 13.8 billion years ago. Our task is to find it, to listen to its vibrations, and to finally decode the fundamental nature of spacetime. These silent threads may ultimately write the final chapter of the universe itself. As a cosmic string network evolves, its loops slowly evaporate, radiating their energy away as gravitational waves. This process represents a slow leak of the universe's primordial power, a gradual smoothing of the flaws that were frozen in at the beginning. But where does that energy go? It disperses into the fabric of spacetime, becoming part of the background hum of the cosmos. In some theoretical scenarios, this is not an insignificant detail. The decay products of these strings, whether they are gravitational waves or even hypothetical exotic particles, could subtly influence the universe's long-term expansion. Think of it as a cosmic budget. For billions of years, the gravity of matter and dark matter has been pulling the universe inward, slowing its expansion. But we now know that a mysterious force, dark energy, is overpowering that pull, causing the expansion to accelerate. What if the final evaporation of all cosmic string loops adds one last critical contribution to that dark energy budget? It is a profound possibility. The same defects that may have seeded the first galaxies could, in their final death throes, provide the final push that defines the universe's ultimate fate. This creates a breathtaking symmetry. The physics of the universe's first second, the era of symmetry breaking and phase transitions, gave birth to cosmic strings. Their gravitational influence may have drawn together the first structures, and then, trillions of years from now, as the last stars die and galaxies fade to black, the last vibrations of the last cosmic string loops could echo through an empty cosmos, their spent energy contributing to the void's final, eternal acceleration. These cracks in reality could be the bookends of existence, their story spanning from the first flash of creation to the last whisper of time. A confirmed cosmic string would shatter the foundation of modern physics as we know it. Our current rulebook for the universe, the Standard Model, is a masterpiece of precision, cataloging every known particle and force with breathtaking accuracy. Yet it is profoundly incomplete. It has no place for the gravitational force described by Einstein, and it offers no explanation for the dark matter holding galaxies together. Most critically, it describes a universe that is stable and symmetric, one where the forces have always been separate. The existence of a cosmic string would be a direct physical rebuke to that tidy picture. It would be a fossilized scream from an era of unification, proving that the forces were once one, and that the vacuum of space itself underwent a violent, imperfect transformation. This is why the hunt is so urgent. Finding one is not about adding another oddity to a list. It is about being handed a key to a door we have been trying to pick for generations, a door that leads to a deeper, more fundamental layer of reality. The Standard Model is a brilliant account of the universe's present. A cosmic string would be a relic from its past that forces us to write a new, more complete story for its future. This fine-tuning of the cosmos is no accident. The very existence of stars, planets, and life itself depends on a delicate balance of physical constants and cosmic conditions. This is the heart of the Anthropic principle, a profound idea suggesting that our universe must possess the specific properties that allow for observers to exist within it. We are here to question the cosmos precisely because its rules permit our existence. Within this grand philosophical framework, cosmic strings take on a new and startling significance. They are not merely potential architects of galaxies, but a critical dial on the universe's life-giving potential. The density of a cosmic string network could have been a decisive factor in the fate of everything. Imagine a universe riddled with far more strings than our own. The gravitational chaos would have been absolute. Galaxies would have been shredded before they could ever form, their nascent stars torn apart by the relentless pull of countless whipping threads. The cosmos would be a dark, sterile void, a cosmic graveyard incapable of fostering any complexity. On the other hand, a universe born perfectly smooth, with no strings or defects at all, might have faced a different but equally bleak fate. Without those initial gravitational seeds, those deep wrinkles in spacetime, matter may have never clumped together effectively. The primordial gas could have remained a formless, diffuse haze, forever failing to ignite the first stars. In this scenario, the cosmic strings we have been discussing are not just possible objects, they are a necessary ingredient. Their presence, in just the right abundance, might have been the golden mean that carved out the galactic landscapes where life could one day emerge. This perspective transforms our search from a simple hunt for a relic into a deeper inquiry about our own place in the cosmos. Are we the beneficiaries of a cosmic lottery where the number of cracks in reality was just right? The answer could be written in the silent, fading network of strings that may have made our universe a home. The raw power contained within a cosmic string is almost beyond comprehension, a potential energy source that dwarfs every star in every galaxy. Yet this power comes with a fundamental and perhaps final caveat. We could never actually use it. The dream of harnessing a cosmic string is a technological mirage, a fantasy that shatters against the unyielding laws of physics. The first and most obvious challenge is its size. A cosmic string is thinner than a proton. You could not build a container for it because there is no material known to science that could interact with something so infinitesimally narrow. It would pass through the atoms of any structure we could ever conceive of as if they were not even there. There is nothing to grab, no surface to attach to, no handle on this thread of power. Even if you could somehow position a facility near one, you would face an environment of pure gravitational chaos. The space around a string is not just warped, it is sheared. The intense gravitational gradient means that the force of gravity at your feet would be vastly different from the force at your head. Any physical structure, any piece of matter, would be torn apart atom by atom, subjected to tidal forces far more extreme than those at the edge of a black hole. There is no stable orbit, no safe distance, only a zone of certain destruction. And this ignores the most profound problem of all, the sheer impossibility of extraction. How do you tap the energy of a flaw in spacetime itself? This is not a fuel you can burn or a reaction you can catalyze. It is a fundamental tension locked into the geometry of the universe. Trying to harness a cosmic string would be like trying to bottle a shadow or store the concept of left and right. The very act of attempting to extract its energy would likely just cause it to vibrate, radiating that power away as gravitational waves, utterly useless for any practical application. This reality check is not meant to diminish their wonder, but to frame it correctly. Cosmic strings are not potential power plants. They are cosmic fossils, natural laboratories, and fundamental puzzles. Their immense power is a testament to the energies that shape the cosmos, a number written into the fabric of reality that we can calculate and marvel at, but never hope to plug into. They remind us that the universe is filled with forces that are not just beyond our control, but fundamentally beyond our interaction, wonders to be observed and understood from an impossible and necessary distance. A cosmic string is more than an object, it is a message. This thread of pure energy is a fossil, perfectly preserved from the universe's first split second of existence. While we dig through geological strata to understand Earth's past, a cosmic string would be the ultimate archaeological treasure, a relic from the dawn of time itself. Every other object we observe, from the oldest star to the most distant quasar, has been processed, transformed, and aged by billions of years of cosmic evolution. But a cosmic string remains pristine. It is a snapshot of the universe when it was less than a second old, its fundamental properties locked in place during that initial, violent phase transition. By simply measuring a string's tension, we would be reading the energy scale of the universe at the moment it formed. Its distribution across the sky would reveal the specific pattern of symmetry breaking that birthed the forces we know today. And its evolution, how it vibrates and decays, would be a direct playback of physics at energy levels 1,000,000,000,000 times more powerful than anything our most advanced particle colliders can ever hope to achieve. This is a time capsule with no equal, carrying data from an era we can only theorize about. Finding one would be like discovering the original blueprint for reality, a first-hand account from a moment before time itself had truly begun to flow. This signature of a split galaxy is a ghost that haunts our telescopes. Many objects in the cosmos can create a similar mirage. A distant galaxy seen perfectly edge-on appears as a razor-straight line of dust and stars, a natural formation that could easily be mistaken for the dark shadow of a string. Even the gravitational lensing effect, the creation of duplicate images, is not unique. The immense gravity of a massive galaxy cluster can bend the light of a background galaxy into long, thin arcs, sometimes even creating multiple copies that could, at a quick glance, resemble a string's handiwork. The universe is filled with these great imitators, and the challenge for astronomers is to perform a cosmic interrogation, to rule out every other possibility. This is not a single observation, but a rigorous process of elimination. It begins with deep, multi-wavelength data. If a candidate line appears in an optical image, scientists will check it against infrared and radio observations. A real cosmic string, a flaw in spacetime, would be completely invisible across all these bands. It would cast the same dark shadow everywhere. An edge-on galaxy, however, would glow with the heat of its stars in the infrared and might show the radio emissions from its core. A lensing cluster would reveal its true nature by the specific way it distorts the shapes of hundreds of background galaxies, not just one or two. Every potential imposter leaves a different kind of fingerprint. The process is painstaking, requiring the cross-referencing of immense datasets from the world's most powerful observatories. It is a testament to the careful, methodical nature of scientific discovery. Finding a cosmic string is not about a single eureka, a moment, but about the slow, deliberate accumulation of evidence, eliminating the ordinary until only the extraordinary remains. While cosmic strings capture our imagination, they are not the only possible scars from the universe's birth. The same violent phase transitions that could have etched one-dimensional threads into spacetime might have also forged other, even stranger, topological defects. These are not made of matter, but are imperfections in the very fabric of the vacuum, each with a different shape and a different set of bizarre consequences. The simplest way to categorize them is by their dimension. A cosmic string is a one-dimensional line, but what about a two-dimensional sheet? This theoretical object is known as a domain wall. Picture it not as a physical barrier, but as a plane where the fundamental laws of physics change abruptly. On one side of the wall, the properties of the vacuum might be set one way, and on the other side, they are set differently. It would be like a soap bubble suspended in space, but instead of separating air from air, it separates two distinct versions of reality. The gravitational effects of such a structure would be catastrophic. A single domain wall stretching across a galaxy would possess such immense surface density that its gravity would violently tear apart stars and planetary systems on either side. If even one of these relics existed within our observable universe, its devastating signature would be unmistakable, a vast, rippling disturbance in the motion of every galaxy it touched. Thankfully, our cosmos appears to be free of these destructive sheets. suggesting that the early universe's phase transitions did not create them, or that they inflated away into nothingness. Then there is the opposite extreme, a defect with 0 dimensions, a single point. This is the magnetic monopole. In our everyday experience, magnets always have 2 poles, a north and a south. You can break a bar magnet in half, but you will always get 2 smaller magnets, each with its own north and south pole. A magnetic monopole would be a solitary north or a solitary south, a fundamental particle carrying a net magnetic charge. These are predicted by many grand unified theories, and like cosmic strings, they would be fossils of a more symmetric age. Their existence would rewrite our textbooks on electromagnetism, and they could have profound implications for the universe's evolution. In fact, the initial theoretical prediction of monopoles in such great abundance was one of the key problems that led to the theory of cosmic inflation, the rapid expansion that likely smoothed them out to an undetectably low density. This family of defects paints a picture of a far more chaotic and dangerous early cosmos. We might have been lucky. A universe filled with domain walls would be uninhabitable, ripped apart by gravitational tides. A universe overrun with magnetic monopoles might have collapsed back in on itself long ago under their collective weight. Cosmic strings, by comparison, seem almost elegant. Their one-dimensional nature allows them to weave through the cosmos without necessarily destroying it, potentially even helping to build the large-scale structure we see today. This broader context makes the search for cosmic strings even more meaningful. Finding one would not only confirm a specific type of defect, it would tell us precisely what kind of phase transition our universe underwent, revealing which symmetries broke and how in that first fleeting instant of time. This potential to probe quantum gravity leads us to an even deeper mystery, the black hole information paradox. At its heart, this is a crisis about the nature of reality itself. According to Einstein's general relativity, when something falls into a black hole, it is lost forever, its information erased from our universe. But quantum mechanics insists that information can never be truly destroyed. So what happens to all the data describing a star, a planet, or a person that crosses the event horizon? Does it vanish, violating quantum law, or is it somehow preserved? This is the paradox, a fundamental clash between our 2 most successful theories of physics. Some physicists now look to cosmic strings as a potential clue. A cosmic string is a one-dimensional object, a perfect line. In the abstract world of physics, information can be encoded along a line with perfect fidelity. Think of it as the ultimate fiber optic cable, a thread that can carry data in its very structure. The speculation is that the physics governing a cosmic string, a singularity stretched into a line rather than compressed into a point, might show us a mechanism for how information could be preserved even under the most extreme gravitational conditions. If information can be stored along the one-dimensional core of a string, perhaps it offers a hint about how the universe might store the information that falls into a black hole, not by destroying it, but by encoding it onto a surface like a hologram. This connection is profoundly speculative, but it underscores a breathtaking idea. These cosmic cracks are not just fossils of power, they might be Rosetta Stones, helping us decipher how the universe maintains its memory, linking the fate of information to the very fabric of spacetime from which it was born. Our search for these cosmic cracks is more than a scientific endeavor, it is a deeply human one. The mere act of contemplating an object that could slice a world in 2 forces a certain perspective. We are not in any immediate danger from these theoretical threads, but acknowledging their possible existence and the raw, untamable power they represent serves as a profound reminder of our own fragility. We live on a tiny, rocky world orbiting an average star in a galaxy that itself may have been woven onto a string's invisible scaffold. This knowledge does not frighten, it humbles. It fosters a profound sense of wonder that we, with our limited senses and brief lives, can even conceive of such colossal entities. With this wonder comes a responsibility, a duty to pursue this cosmic knowledge with care and intention. Our goal is not to one day harness this power, an endeavor we have seen is likely impossible, but to simply understand. We seek to learn where we came from, how our universe grew from a hot, dense point into the complex web of galaxies we see today. Every observation, every theoretical calculation is part of this grander quest to find our context. Are we a fortunate accident in a cosmos of chaotic power, or is our existence written into the very flaws of reality? The ethical weight lies in using the answers not for domination but for wisdom, to better comprehend our fleeting, precious place in the infinite scheme. The theoretical landscape of cosmic strings reveals a universe far stranger and more powerful than our everyday experience suggests. Our journey has traced their origins to the universe's violent birth, followed their potential to shape the cosmos, and listened for their whispers in gravitational waves. These one-dimensional cracks are more than just defects. They represent a pinnacle of theoretical physics, a testament to the hidden machinations that operate on scales both unimaginably vast and infinitesimally small. They challenge our definitions of matter, energy, and even reality itself. While their tangible existence remains just beyond our grasp, hovering in the realm of prediction, the very pursuit is what pushes science forward. The hunt for these cosmic titans drives us to build better telescopes, to listen more carefully to the ripples in spacetime, and to refine our most fundamental theories. This relentless curiosity is a reminder that the cosmos is brimming with profound wonders waiting to be uncovered, mysteries that demand we look deeper and think bigger. What do you believe is the universe's most powerful hidden force? Share your thoughts on these cosmic titans in the comments, and subscribe for more journeys to the very edge of understanding.